So one of those things is the Pauli exclusion principle. So Pauli was a scientist, and he basically had said that in an orbital can be either unoccupied, meaning there are no electrons in it. There could be one electron in it, or there could be two electrons in it. But there can't be more than two electrons in each of the orbitals. So each orbital can only hold two electrons. But the subshells, right? So the S subshell has one orbital. It holds two electrons. S holds a total of two electrons, right? P holds a total of how many electrons?
Six.
Okay. Good job. Let's see. So we'll go.
I don't understand this stuff.
Okay, so we said the S, we said it has one orbital, and it can hold a total of two. And then we said P has how many orbitals?
Three, I guess. Three.
Three. And it can hold six.
Yeah.
We have D has how many orbitals?
5.
And it can hold how many?
10.
And F?
7.
And it can hold how many?
14.
Okay, are you guys with me?
Yeah.
Yes.
So Nate asked, can't have two until you have one either. Yeah, that's right. So you have to have at least one in there, and then you'll have the second. We're able to put the second. Okay, so again, it's always going to be based upon lowest energy level. That is the concept, okay? So we want to try to keep a low energy level, and we know that by putting into the lower orbitals first, right? And then we'll get up to the higher orbitals, right? So it'll put electrons in lower and then builds its way up. You guys
Well, Dr. Henry?
Yep.
I'm sorry to stop you here, but I don't know if I'm jumping the gun. Right now, I'm lost because right now you just finished talking about the Pauli something principle, and that one, you could only have a maximum of 2 electrons, if I'm not mistaken. And here we're talking about P with 6 electrons.
No, it says you can have a maximum of 2 electrons per orbital. How many orbitals are in the P?
Okay.
So there's three orbitals, right?
Yes.
So altogether it holds 6. So we can have six electrons total, but only each orbital in the P can hold 2.
Okay, I get it now.
Does that make sense?
Yes, thanks.
Okay. Good question, though. That is, it is a little confusing because, you're like thinking, didn't you just say, but you got to think about orbitals are kind of like little seats in those subshells. You're sitting in the P section. The P section has 6 seats, but there's 2 that are 3 orbitals there, groups of 2 together.
Yeah.
Okay.
Yeah.
So how do we determine the amount of orbitals? Well, it's kind of if you kind of look at the trend, right? So the number of orbitals in the S is the smallest one, is 1. The number of orbitals in the P is 3. The number of orbitals in the D is 5, right? But you also can kind of take a look at the periodic table, right? You know that you're able to hold a total of 10 electrons in the D, right? If we look at our periodic table, let me pull up a periodic table. Okay, so if we look at the D orbital, there's 2, 4, 6, 8, 10. So there's 10 electrons that can be held there. We know that every orbital only can hold 2 electrons. So then how many orbitals do you have?
5.
5. Okay.
Yeah.
So the maximum orbitals in the D shell is it's going to be 5. And so if we went higher than that, let's see, go back to my slide. If I went higher than that, let's say we went to, oops. So if we happen to start discovering more atoms and everything like that, and we end up going to the G subshell, how many orbitals would we expect the G to have? 9.
9. Yeah.
And it would be able to hold how many electrons?
18. 18.
Okay. And then the H.
Sorry. So every orbital in the group would be able to hold the same amount?
No, every orbital can only hold 2 electrons at max.
I mean, every element in that group would have the same orbital. So like, even if it's at the beginning of that group, it will have 5 orbitals.
Yeah, so the fact is that those seats are there. The question is whether there are electrons in those seats.
I got you.
Okay. So the orbitals are kind of like these are the seats that are going to be available. So there'll be 9 orbitals that would be in the G subshell, right? So there's 9 groups of seats together.
But then what the element is how many fill that orbital?
Yeah, so the element is like by looking at the element itself, right? Depending on how many electrons it has, it can fill up that orbital, right? And again, we're thinking about ground state. Ground state meaning the lowest possible energy that we can get, right? Not excited state, because what can happen is that we can excite those electrons to be in a higher state, but then eventually they're going to have to come back down. So that eventually they'll have to come back to the seat that they were trying to.
All right, thank you.
Okay, so we've got to look at it like this. So when we're talking about electron configuration, we're talking about the electron configuration for that atom or for an ion, right? So we're trying to determine where exactly those electrons are in that atom. And we're trying to keep a running total, an account of all. Okay, so if we're talking about a specific element or a specific atom or a specific ion, then we're talking about the electron configuration for that ion. Now, other elements could have those same numbers, but no 2 electrons in an atom are going to have the same location. Do you know what I'm saying? Or the same orientation. Does that make sense?
Yeah, that makes sense.
Okay. Okay, so this is just a nice little figure that kind of talks about everything that we've talked about at this point and kind of showing you, okay, there's the 1s, there's the 2s, there's the 2p. And you guys all remember that when we get down here to the D, we start off at 3D. When we get down to the F, we start off with the 4F. Make sense?
Yeah.
Okay. Clear.
D, 4F.
Okay, so this is just, so they were just actually looking at the energy level of electrons, so the energy density of electrons as they're circling the nucleus. And so we're able to detect them under certain circumstances, and this is what that shows. So this just gives you an idea of the energy diagram for that sublevel, right? So, and you guys already know about this. So if we're talking about hydrogen, well, 1s1, right? So this tells us the principal quantum number. This tells us the subshell, and this tells us how many electrons are in that subshell, okay? And so this is basically showing us the electron configuration for some of the atoms that we're looking at. Now, you'll notice that we're using that core. You guys, we've talked about the core, right? Using the core.
Yeah.
Okay, and so the core helps us out quite a bit on so many levels. it keeps us from making those little mistakes. But you'll always pay attention to, well, these are all neon, because neon is the noble gas that is right before these particular atoms. And so we use that as a core. We're saying that all of those electrons in neon are completely full, and then this is the one that's left over. Now this electron, this here, this one electron in this case, is called your valence electron. And so we're able to sit there identify our valence electrons by putting the item into a core, and then the ones that are left over are the ones that we could basically use for a reaction. Okay, does that make sense?
Yes.
So helium cannot be used overall then.
It's not that helium can't be used over, you're saying as a core?
Yeah,
You can use helium as a core because helium is full, right?
right.
Okay, so then what we would do is, in that case, in the case of lithium, it'll be just, you could write it as Li He. Yep. And then we'd have to put the 2s1, right? So we could write it that way. But in this case, there's no benefit of using the helium one, because really it's the same thing as writing the 1s2, right? Because that's all that helium is just 1s2.
Oh, okay. I was
that make sense?
practicing on all these configurations last night, and I got one for helium. I was like, wait, can helium be used for one?
Yeah, it can be. I mean, but it's like, as scientists, we know we like to do things that we're lazy. Okay, I'm going to be honest. We're a little lazy. We try to find shortcuts to make it a little bit easier. And after you write the electron configuration for, like, let's say, lawrencium. Where's lawrencium is located at?
Yeah. Let me get my periodic table.
It's somebody give me the atomic number for lawrencium. Anyone?
103.
103.
103. Okay, so now you're keeping track of 103 electrons. Do you want to start off at the 1s, 2s2, 2p? You know?
No,
No, you don't want to write those all out, right?
but it's worth it.
Well, yeah, it can be worth it, but if you could write it down smaller, would you want to write it down smaller? Right?
Yeah,
Yeah.
shortcuts.
Exactly. So it kind of keeps you from making a lot of those simple mistakes, right? Yeah.
There
so
are
in that
shortcuts
case,
available then.
So if we were doing the LR, right? So then it would be LR.
LU.
So what would be the noble gas?
LU.
LU?
Someone says RN.
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 Okay, RN. Okay, and then what would be next?
7s2.
7s2. Okay,
And then 7d9.
60.
6D.
ooh, this is a good one. Okay, let's pull up the periodic table so you guys can see.
I'll be honest, that's a good trick right there.
What do you mean by it's a good trick? It's not
Well,
a
it's
trick.
no, it's a tricky by getting the incorrect answer.
Ah, okay. So if we follow it, so we have radon as our core, and then we go here to 7s. Now, where is 79? I mean, where is 89? Because
Okay.
where's 89 located?
It's in that gap.
I can't see it.
Okay, so it's
Okay,
down here,
okay.
right? Isn't it
Yeah,
in the F?
down. Yes.
So literally, we need to do this. We need to go from here down to here. So what is this? If this is 4F right here, so what is this guy down here?
5F.
5.
5F. So then it would be 5F.
That would be 7, 5f.
Okay, so how many would be in the 5F? So it would be 7s2, 5F, and how many would be there to get to this point, to this guy?
Here's my calc.
15.
So are there 15 in the F orbital? We've talked about this.
No, there's
14?
There's 14, right? So 5F14, and then this guy here is really located
In the 1D?
in the D. It would be the
Oh,
1D,
D.
or would it be the, so this is
16.
3, 4, 5, 6, 60,
Oh, yeah, 60.
61. Yeah, and I always use this one on an exam, just so you know. Oh,
That's
did I say
confusing.
that out loud?
Wait, can you explain that again? How did it go to 4F? Wouldn't that be?
Because look where it's at. Look at the number. We're following the atomic numbers,
Oh,
right?
I got that, but why does F start at 4?
It starts at 4F. This guy is 5F. Remember, there's a drop. Remember, we've kind of talked about it. We have 1S. Is there a 1D or a 1P?
No.
No, there isn't. Then we go 2S, 2P.
Right.
Is there a 2D?
So no.
Then we go
3D.
3S. There we
3S.
go. We go 3S, 3D,
3P.
I mean 3P, 3D, 3D.
Doesn't it go to 4S and then 3D?
I thought it's 4S before 3D.
No, we
Yeah.
do in terms of energy, but in terms of the orbitals that are technically available in that energy level, in the 3, there's only 3, S, P, and D, right? We don't have a 3F, do we?
Okay.
Okay.
No.
But you're right. There is, we would go 4S first because 4S is lower in energy. Okay.
Mhm.
Then for the fourth level, we have a 4S, we have a 4P, we have a 4D, and we have a 4F.
4F.
Right? And then for the
Yes.
fifth, we have 5S.
See that 4F, where did that 4F come in?
Okay, so if you notice, right? Do you see a 3D here? I mean a 2D,
Yeah.
right? So
No.
every time we're adding another sub-level, right? Another subshell. Here we added the 2P, right? We added the P, right? So the first one, we only have the S. The second one, we have an S and a P. The third one, we have a S, P, D. The fourth one, we have S, P, G, F. So what's going to be in the fifth one?
Oh, so it starts at 4 because of like sequentially where it's at.
That's right. Because we're adding another level to add more electrons.
So you wouldn't start back at 1. You just keep going
Well,
up.
No. You're going to start, like, every atom has to start. Like, say, we're talking about Lawrencium, right? So in that case, it's going to have all of these electrons, right? So all of those are going to be accommodated by that radon. Radon. So everything is going to be accommodated by that radon up until the point that we get to right here, right? So all of those other electrons are already taken into account by us putting in radon. Does that make sense?
Yeah.
Okay. Rather than writing out 1S, 2S, 1S2, 2S2, 2P2, 3P, rather than writing all of these guys out, we could just simply write down radon and then start from right there. Okay. Does that make sense?
Yeah, I guess I just was confused about the jump up to 4F, but that blue line shows that it actually goes in the chart, like up in that other spot. Is that correct?
Mm-hmm.
So yeah, I guess it makes more sense.
Yeah. And if you also pay attention to the atomic number, because you want to follow the order, it's 87, 88. Then we go down here, 89. Well, we know that this is the F orbital, right?
Right.
Okay, so that's the same thing here, right? We went from the 4S, then we go back down to that 3D. So we know, because I told you guys that this is right here is the 3D, right? So those other, like these guys here, these guys are called like degeneracy, right? So they kind of there's an overlap. Really what happens is that there's an overlap in energy between the 4s and the 3D because these shells are so much bigger. So you have electrons that are kind of overlapping in energy with the electrons that are here, right? And
Right.
so even though this is because if we look at it, right, remember I told you that as we go down the periods, they're kind of like the dolls, but in other words, you're kind of sticking a whole bunch of stuff, a whole bunch of like electrons between that 4, that 3, and that 4. And so those 3D electrons are kind of overlapping with the 4s, okay? And so it makes that 4s a little lower in energy than that 3D level.
Dr. Henry, I'm
Yep.
confused. Where's 3D on this periodic table?
3D would start right here,
Okay.
okay?
Right where, is it where 3 is on the row of 4?
That's right. So it's 4, and then this would be 3D, right?
Okay.
Because is there a D? Do you see a D out here anywhere?
Where?
Yeah. So these guys, remember, these are the noble gases. They're stable, right? So what happens
Okay.
is the third energy level is located, even though, so the third period represents the energy level. But
Okay.
really what's happening is that you're putting these electrons in that energy level, right? And they're doing their orbit. Well, these guys are a little bit higher in energy than the orbit for 4s, because 4s is real simple. It's just a little circle. It's a not a circle. It's a ball. Right? It's a sphere. Okay. Now,
Yeah.
if you guys remember the D, let me show you what the D looks like. I can't show you the F because the F is just a hot mess. So here, you guys mind if I erase this and then we'll go back to it?
Don't mind.
Okay, so here's the S, here's the P, and here's the D, right? So the S is real simple. It's just a sphere. Well, the D is a little more complicated, right? And so because of its complication, that 4s has a lower energy level than the 3D, okay? And it's just a little bit lower than the 3D, not too much. And so we fill up those electrons first, and then we go to the 3D, okay? So that's the reason why it shifts, because it helps us remember that, oh, the D is a little bit higher in energy than the 4s, okay? And then, and then the 4f is a little bit lower in energy than the 7s. I mean, a little bit higher in energy than the 7s.
Okay.
And then it's lower than energy than the, sorry, not the 7s, than the 6s, sorry, than the 6s, because it would be right here, right? So it's really located at this point. So it's lower than the, a little bit higher than the 6s, but it's a little bit lower than the 5D.
So
Okay?
on that Lorentzium, why did you go back to D right at the very end?
So because, let's go back to the periodic table. Okay, so let's go through Lawrencium, right? Here's Lawrencium. You guys see it at the very bottom?
Yeah.
Okay,
Yes.
so we start at radon, then we go to the 7s. Oops, sorry, getting ahead of myself. Rn, 7s2. Okay, so then look at the atomic number. This is 88, so that means we're going to go down here, right, to find where 89 would go. So we go all the way over, right? And if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, right? Because there's only 14 electrons in the 4s. So then it would be 5F14. And then look, the Lawrencium is actually just acting as a space holder, right? Or Lawrencium is really in the D, but since this guy, the way our periodic table is set up, it's set up so that we can actually see it. What it really looks like is this. Okay. So Nate, these two, the LU and the LR, are really in the d orbitals. And that's where we're sticking in. We're stuck in all of these guys in that spot, that blue spot that was there, right? So that it makes it easier for us to see the periodic table on one sheet of paper rather than having to use a big sheet of paper to look at the periodic table. Does that make sense?
Yeah, that makes sense.
Yes.
Makes sense.
Okay.
So Dr. Henry,
Mm-hmm.
so before you had erased this,
Uh-huh.
and I don't know if this might help for other people who are like visual learners like me, but and when you do the pattern, when you actually write everything out, it always makes a pattern. Like it actually makes like almost like a pyramid pattern. So then the 5S2 section would, if you were to write all out, if they were doing the same thing for something even lower, it would be the whole 5S2, the 4Ds, and then the 5P. And I know that if someone saw that way, it would throw them off as well. But it's always, and then if that was to go to the end, and it even end with the G section if there was one, right?
That's
Before
right.
you had actually, okay.
Yep. Yes, you didn't know chemistry is all Illuminati, right?
Well, if it is, I want out.
No. You guys have already been implemented, so you guys are all part of it now. Okay. Okay, are you guys good? Good understanding so far?
Yes.
Okay.
Fairly.
Did the exam have the majority of electron configuration problems? Because this is easy. Can they?
Is that a yes, Dr. Henry?
I'm not saying yes because I'd be lying.
That's a no then.
It's not that easy though.
Okay. Okay, so let's do one more and then we'll move on. And then we're going to start talking about ions and why ions are going to be forming and all that good stuff, right? Okay, so I'm going to make it a normal looking periodic table. That's what you guys are going to see in the exam. Let's see, maybe. Okay. Sorry, it takes a little minute. Okay, so let's do.
I'm sorry, someone who has like a flute or flute sounding, can you mute your mic?
Okay, so let's do EU. Okay, so first thing you want to do is figure out where AU is located at.
Found it.
EU, where's it located?
Wait, is it AU or EU?
Yeah.
EU.
That I think it's the Anticynides side.
Give me the atomic number because otherwise, or you can give me the.
63.
63.
63.
Okay, 63. Thank you. Yes. Or you want to tell me the period or the group, although it's kind of hard since it's in that F.
Period.
Yeah, period.
Mm.
You guys should know what the periods are at this point and what it means. Okay, so we're doing EU, which we know is 63. Somebody circled it in yellow right here. Okay, so what is the noble gas that would be before EU?
Xenon.
RN.
RN.
Ooh, so this is a good one. Are you sure it's RN? Somebody says xenon and everybody else says RN.
R.
I
It's
think it's
RN.
Yeah, RN.
You want to put money? That is
No,
before.
it's XE.
Oh.
Oh.
Yeah, XE.
Okay, now I'm
Okay,
confused.
so it's Xe. Good job for that person who said xenon. Okay, so we have Xe, and then
6s2.
6s2. And then
5d.
No, it's 4D.
ooh, okay. Are you sure it's 4D?
Well, Dr. Henry,
It should be 5d because the first one is 3d, is it not?
Okay, follow the road. Okay, so we go here. Are we in the D or are we in the F?
Dr. Henry,
Yes,
Oh.
ma'am.
I'm really, really sorry.
Oh.
I don't know how xenon is the noble gas for that.
It's because it's number 63 and RN is 86.
Okay,
Thank you.
I
It's
see.
the
Yeah.
placeholders that's
Thank
throwing
you.
everyone off.
Exactly. It's those
Yeah.
placeholders. That's why
So
I'm
you
trying to
gotta-
get you guys used to it, right?
Yeah.
Do you see that, Barry? What he was saying? So if you actually, and that's a very good point. If you look at the atomic number, well, we were at 63. We know that radon is 86, so that would be after it. It wouldn't be before it. So you want the noble gas that would be before it.
Yeah.
Okay. So if we followed the atomic numbers, that's 55, 56, and then we come down here to the F. So it would be what?
4f7.
Or F7. That is correct. So there would be nothing in the 5D, right? Because this is the 5D right here. Right?
Yeah.
Okay. You want to do one more?
Wait,
Yes.
real quick though.
Yes.
The 4F7, the 7 is just how many it takes to get over to that one, right?
That's right.
Okay.
1, 2, 3, 4, 5, 6, 7. Yep. So it's where it's located in that F subshell. It tells you how many electrons are in there. You're never going to have more than what it can hold, right?
Yeah. Okay.
So you'll never have more than how many electrons can be held in the F subshell?
14.
Oh, and the F,
14.
14, right?
That is correct.
Okay, I'm starting to see it now.
Okay, so you want to do one more?
Yes.
Yes.
Yeah.
Okay, so let's see. Let's do. Let's do plutonium. PU.
94.
Something. PU. Okay, Yari, are you there?
Yes, sir.
Excellent. So what would be the noble gas for PU?
Radon.
Good job. What about, let's see, Wilmer? So what's going to come after radon? So we're right here. We're moving. This is where we're going.
S7.
7s2. And that would be 5f6. 1, 2, 3, 4, 5, 6. Okay, questions?
Man, bro, I'm still kind of confused on like how you get the like from the plutonium to the to the gas, to the Rn? Like what determines that?
So there's a couple of ways that you can do it. Somebody had made a point. One of the best ways of looking at it is looking at the atomic number.
Okay.
Okay, Pu is 94, right? You want to find a noble gas that would be right before it. So in this case, would it be 86 or would it be 118? Because these are the noble gases.
Oh, so it's just the next. Okay, I see. The next one that it. I got
That
you.
would be right before it. Yeah.
Yeah.
Because again, the
Okay.
noble gases represents those are what we call cores. They're filled, they're happy, right? And so this tells me, okay, so these electrons are not going to be able to be used because they're already happy, right? They're already matched up, they're all nice and full. So that means that we can use these guys. These guys are going to be my valence electrons. Okay.
Okay. Okay, I see it.
Dr. Henry.
Yes.
Okay, if I'm not mistaken, there are 8 valence electrons for this Pu. There are
Can you
8
repeat?
valence. I said, if I'm not mistaken, there are 8 valence electrons for this Pu.
That is correct. Yep.
Okay, so doesn't that mean it is stable?
No, because part of being stable is you want the right 8 valence electrons, right? And so a quick way of doing it, because you're thinking about just the Lewis dot structure, octet,
Okay.
8, right? So
Yeah.
what you would want is you'd want 7p filled as well. So you'd want 7s
Okay.
all the way up to your 7p
Wow.
also full, right? Because when you're thinking about your octet rule, you're just looking at the S and the P.
Okay.
Right, and that's part of the thing that makes the transitional metals a little more complicated, and the actinoids and the lanthanoids
Okay.
metals. It makes those guys a little more complicated because your first instinct is saying, oh yeah, octet 8, and so those guys have the D's and the F's, right? So those are empty shells that need to be filled before you get to that, because they're at a lower energy level.
Okay. Okay. So this is for only the transitional metals and these lanthanoids and actinoids that are this complicated. Is it those 3 guys? Only those 3 guys that are complicated?
Yeah, these guys are complicated. Yes. Yeah. Because the other ones are not so complicated, because here this is the S, right? So if you lose 2 electrons from there, you only have 2 valence electrons in this part here to work with, right? So those are pretty easy. And then these guys get pretty easy because everything else is full on that in that regard. And so that makes your nice 8. So when we're talking about octet, we're talking about the S and the P when we're talking about that.
Okay.
Octet meaning 8. And we're going to talk about that, what that means here in a second. Okay.
So we got the 8 valence electrons because we added the S2 and the F6 together, those electrons. Is that right?
No, so what she's asking, she says, yeah, so we have a total of 8, yeah, because there's 2 here and there's 6 here.
So
right?
what happened to all the electrons before radon?
So all the electrons that are before radon are incorporated in there, right? Those electrons, they're good because they're full, right? They fill up all the way up to the radon shell, right? So those guys are kind of like in a locked vault. You're not going to mess with those unless you absolutely must do it. You don't want to touch those. That's kind of like that money that you've been saving for years and years and you never want to go to. But this money, is the stuff that you can actually use. Right?
So the noble gas locks up all the electrons that came before it?
Yeah, so what happens is that there's an amount of stability associated with you being that noble gas, right?
Right.
And so basically you're kind of paying into the amount of energy that's associated with being that noble gas right here. So all of those electrons are kind of like, okay, so these are the electrons that would make me a noble gas, right? and these guys are extra, right? So we need to figure out what we're going to do with these extra, right? So one of the possibilities is that we could try to get like the next noble gas, or we could try to lose electrons to be like this noble gas.
Right.
Okay. So now I was saying to Mary, and I'm kind of saying it to all of you, is that when we talk about the transitional metals, they're a little complicated. There's a little more that we need to know about them to kind of understand how they use all of their valence electrons. But when we talk about our alkali metals, our alkaline metals, and we talk about our non-metals, these guys over here, okay, all of these guys over here, post-transitional metals, those guys, they're a little easier to understand and how they're going to behave, right?
More
Where
straight.
these guys are kind of a hot mess, right? Part of the reasons why they're called transitional metals, hot mess.
I was just wondering what happened to all the electrons before, but basically they're taken care of, and that's why we indicate it with a noble gas.
Exactly.
Okay,
Yeah.
that makes
Okay.
sense. Thank you.
And that's also why we call this our core, right? Makes sense. You're not going to call something that's kind of crazy in your core, right?
Right.
And so the problem is that, so right now, this is our core, and these are the ones that we have to use for reacting. And so this is what we're kind of building up to, because chemistry is all about stability, right? Ultimately, trying to get to be like a noble gas. So this guy, Pu, would have the opportunity or the chance to try to be like a noble gas if he got rid of all of these guys. Or if it gains a whole bunch more electrons and try to get like, and we're assuming that this guy is going to behave like a noble gas, if we ever find what it really is, okay?
All right, thank you.
Okay, questions, concerns?
Oh, I
Okay.
kind of have a question about the d orbital.
Okay, yes,
So you know how you said 8 valence electrons, right?
yep.
How would that work for those in the d orbital, since that can go up to 10?
Then you could have up to, technically 10. So I understand what you're asking, right? So you're saying, let's say we did, let's say zinc, right? So let's write the electron configuration for zinc. This is why everybody likes to avoid the transitional metals. Again, complications, right? Okay, so what is the noble gas?
Argon.
Okay. And then what do we have following it?
4s2 3d10.
Let's do 3d10. Okay. So the d orbital is a kind of a, it makes it a little messy, right? Now, in terms of valence electrons, zinc would be a special case because now we've completed that 3D shell, right? 3D. That is the total number of electrons needed to complete that whole energy shell. So we had the 3s2, we have the 3p6, and we have the 3d10. Right? So in theory, based upon our normal thing, we would assume that, okay, wait a minute, hold on. This guy here would mean that I have, technically, I would have 12 valence electrons, right? Which is, it's possible that you could have 12 valence electrons, but since this guy completes this energy level, since it completes that energy level, it's going to say, okay, this is kind of like me having just these two guys filled, and kind of like me being like a noble gas. So it's not going to want to take from us, right? So what it's going to want to do is just use these two as a valence electron, okay? Rather than using the 3D, okay? That 3D10, because that 3D10 is completely full, right? It's
But
all the way
isn't
filled up.
Isn't the 4s also full?
Yeah, it's the 4s2, but that energy level isn't completely full because if you look at the 4s, we have 4s2, we have 4p, and then
Okay.
technically what we have none there, right? We saw that
Yeah.
4p, and we have the 4d,
Okay.
and we have the 4f, right?
Okay. Okay.
So, which we all have none in, right? There's no
Yeah.
electrons in those guys. So this guy isn't completely full. So it's going to try to find a way of trying to make itself completely full or to get rid of electrons, right? And so what it'll do is, since it recognizes this as being under that lower energy level, it's going to be like, okay, so I only have 2 valence electrons. Do you guys see that? Where if we talk about, let's say we talk about iron. Okay, so if we write the electron configuration for iron, Fe, it's going to be argon, 4s2, 3d 1, 2, 3, 4, 5, 6. So 3d6. How many valence electrons does that guy have?
I can't see the number on top of 3D. Okay, that's 8.
Yep, so it'll be a total of 8 electrons, right?
Yeah.
Because that D isn't completely full, so it can't be included as a filled up and leave it alone. So you're not going to pack it away. You know, in this case, you need to try to figure out a way of either filling this guy up or getting rid of all of them. Okay.
Did you
Does that
get
make
8
sense?
by adding 2 and 6?
Yep,
Oh, okay then.
because that tells you how many electrons are going to be available for reacting.
Oh, okay then.
But for zinc has 2 valence electrons.
That's right. It would only consider to be have 2 valence electrons because we filled up that 3rd energy level completely, right?
Okay, yes.
Does that kind of make sense?
Yes,
I know
it
it's a
does.
little confusing.
Yeah.
You know, that's the reason why a lot of people are like, hey, we're just going to deal with the S and the P orbital, and then that's all we're going to talk about in terms of valence, right? That's why, you know.
That's what they did in high school.
Exactly, because it gets a little confusing. It's a little, you know, crazy.
Yeah.
Are you with me, Yari?
Mm.
Can we do another example?
Can we do another example? Sure. Sure. Okay, so let's see. Let's do. Okay. Can I clear all of this? Did everybody get this down?
I did.
Okay.
Just screenshot it.
Okay, so you got to screenshot it.
Yeah.
Did I erase it before you got to screenshot it?
No, you didn't. I screenshotted before you erased it.
Okay, so let's do CD. So Veronica, if we could turn peanut butter to gold, boy, that would be great.
Said that we were to like hold it like this for like thousands of years, the heat will eventually turn it into gold. Is that true? Or
my God.
In other words, he's trying to say that there's a possibility of it decaying, but there would have to be an element of our choice that's in there to kind of get us. No, not quite so much. So, okay, so CD. Where's CD located at?
CD.
48.
Okay, so we're located here. So if I was writing my electron configuration, what would I do?
Krypton is your noble.
Okay. Okay, and then?
5s2.
5s2.
And then it'd be 4s. 10.
4D10.
4d10. Okay, so what is going to be my core, and how many valence electrons will I have?
Your core is krypton.
Okay, krypton
And
is
you
4.
Yeah, and you have 2 valence electrons.
Okay, so and they are located where?
Sorry, what?
They are located where?
The valence electrons.
Yes, the valence electrons are located where?
And the outermost
Well,
shell.
That's
That's right.
5s2.
That's right. They'd be located in that outer shell, which is at 5s2, right?
Okay.
So this would be our valence.
Okay, so 4D is filled up, but we still have F.
Yep.
For 4. So does it still apply here? Because we still have like 4F left.
So yeah, so you're actually right. So technically the 4D isn't completely full. So they're technically
Okay.
12, right? So you're
Okay,
correct.
okay.
So there would be 12 valence electrons. So it would be the 4D as well. Because we still don't have the 4F completely full.
Okay.
Okay?
Yeah.
Okay, so now let's kind of talk about this, right? So this brings us to those valence electrons, electrons that can be used up for things. So we're going to talk about, I'm going to give you guys another example, and then we'll get to it. So let's say we have potassium. Where's potassium located? What is the electron configuration?
19.
Potassium is 19.
Yeah.
Okay, so it's 19, and so my
Argon.
noble gas,
Argon.
For
Argon.
S1.
Yeah, that's argon.
Okay,
And 4S1.
okay. Okay, so how many valence electrons does potassium have?
1.
1.
1.
Okay, how far is potassium from being a noble gas?
Just 1.
1.
So it's just 1 away from being a noble gas. So
Yeah.
potassium, because it's 1 away from being a noble gas, it's going to want to sit there and basically do what to that 1 electron?
Give it out.
They want to get rid of it.
Oh,
So it wants to
my
lose that electron. And if
Yeah.
it loses an electron, it becomes positive, right?
Yeah.
And then its electron configuration will be exactly like argon, right?
Okay.
So if you lose an electron, this guy's called an ion. And specifically, it's called a cation ion, which is a positive ion. Okay?
Mm.
You get it? Positive cation,
Yeah.
meow, cat.
I don't think anyone gets it, Dr. Henry.
Are you serious?
I got it,
Yes,
Dr. Henry. Don't worry.
I get it.
I couldn't
That was a
actually.
really bad joke. Okay. So if we take a look at something like chlorine, what is the electron configuration for chlorine?
9. 9.
Okay. You said 9.
9. 9.
Neon first.
Okay, neon. So we want the electron configuration. So we want neon first.
Is it neon or helium?
2.
Because
Look where chlorine is located at, Mary.
Okay, I thought you said fluorine actually.
Okay.
Yes.
Oh, so that's why you kept saying 9. I'm like, what?
Yes. Yes.
Chlorine. Okay, so we have neon, and then we have what? After neon,
3S2.
3s2.
3s2. And then
P5.
3p5.
3p5. Okay. So how many valence electrons does chlorine have?
7.
7.
That's 7. Okay. So chlorine has the option of losing 7 electrons or gaining 1 electron and becoming like argon.
8.
Two.
So
It
would
will
it
gain.
would it gain one because it's closer to 8?
Positive
That's
Yeah,
one.
it will gain one.
That's right. Exactly. So it's always going to go the easiest way to go. It takes a lot of energy to lose electrons. It takes a lot of energy to gain electrons. So it's going to try to find the easiest way to do it. So it's going to say, okay, it's a lot easier for me to gain 1 electron than to lose 7 electrons and be like neon. So it's going to be
Negative.
negative. That's right. And so we'll just write it out like this.
3s2, 3p6.
Okay. Or we could also have written it out as
Argon.
okay.
Yeah.
Wait, what?
Wouldn't it be plus Cl plus Ar?
Oh, I see.
No, because you're gaining an electron. When you gain an electron, you're adding a negative charge, right?
Yes.
Okay.
And when you lose, it's positive.
That's right. So this
That's not confusing.
and ion. Okay. So you guys good so far?
Yeah, I'm good.
Okay. Okay. The cation and an anion. Okay. So the way it is, and it's gonna sound really weird, and I'm gonna take you through it a little bit. When you're removing electrons, you always want to remove from the highest energy level, right? So if we're talking about the highest energy level, we want to remove from that first. Then we go to the next energy level, okay? So like say, for instance, let's say we had manganese. Okay, so oops. So if we're writing the electron configuration for manganese,
Ar or argon.
okay,
4s2, 3d4.
No, that one's 3d5.
there we go.
Oh, excuse me, sorry, 5.
Okay, now I don't know why it's 3D. I know.
Okay, Mary, remember
the middle section?
the middle section always starts at the 3D,
Okay.
okay? Always.
Okay.
And then this section down here always starts at the 4F. That's
Yes.
never going to change. So that means the next one is going to be the 4D. This guy's going to be the 5D. This is 6D.
Okay.
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 Okay. And so let's say we were going Mn 2 plus.
2 plus.
Okay. 2 plus means what?
It has lost 2
You
electrons.
lost 2.
It's losing 2 electrons.
Yes.
So our core is going to still be the same. And we're going to remove 2 electrons. We're always going to remove from the highest energy level. So we're going to get rid of this guy first, because that's the highest energy level. So then we'll just have (3d5).
Now, is it the highest energy level because it's the first directly after the noble gas?
No, it's not because it's the first. Well, it just happens to work out that way, but it's because it's at another level, right? So remember when I told you the 3D? 3D is really at the third energy level. And so technically the 4s is lower in energy, but it's really easier to get to that than it is to get to that 3D, because 3D is really complicated. And so you have electrons that are flowing in between that and all that stuff. So it's a lot easier for it just to grab that 4s, right? Because it's at 4 rather than a 3.
Okay, so it's the higher the number.
That is correct. That you're going to
Okay.
remove from first.
Okay.
Okay. So let's say we have, let's do tungsten. Okay. So we're going to have W, and then we'll have W3 plus. Okay. So what is the electron configuration for tungsten?
Xenon.
Xenon.
Xe.
Okay.
6s2.
6s2.
4F10.
Isn't it 4F14?
There you go.
Yeah.
We're
My
at
bad.
14.
Then
And then
wait, 3 more. 5D4. Woo!
Wait, is it 4 or 5d3? Like,
no, it'll be 4 because remember,
okay.
1,
There's
2,
still
3, 4.
tritium.
Mm-hmm.
Well, I don't get it. 4F. Why? 4F. Why?
What was that?
Why 4F? Because you said from the,
Okay.
I think the last
Follow,
anoid.
follow, right? So if we're going, Mary, again, follow. We're
Okay.
going to xenon. Then we're going
Okay.
here. And then we go down
Okay.
to here, to the 4F, right? And then we go back up to here.
Why did you move like that? You know, actually, you not attend the class that you talked about this, probably because of one of those times I had a connection problem.
Yeah, but we've also talked about it today, Mary, because remember, what does this periodic table really look like? If we had to widen, remember?
Okay, yes. I'm actually getting it now.
You say you're actually kind of getting it now?
Yes. Actually, it's the atomic numbers I'm using
That's right.
to get it.
If
Yeah.
you have the numbers, it'll actually
Yeah.
give you the right answer.
Yes. Okay. Thanks for explaining that to me.
Okay, so are we good? You guys
Yes.
are with me? Okay, so now
Brianna's
we're going to lose 3 electrons. Where are we going to take the electrons from?
The highest.
Are we going to take them from the 6s and the 5d?
That is correct. Yes. You guys are making me, I'm getting hot flashes now. Wait a minute, I have a fever. I'm so excited here. Good job.
Yeah.
Yeah, so we're going to take it from those higher numbers. So we're going to get rid of, I'm going to draw my other one here. Again, going to get rid of this guy, and then we're going to subtract 1 from that guy.
From 5D.
Yeah, so you're going to be left with the 4f14 and 5d3.
Yep.
Mm-hmm.
Okay? You guys got it?
It.
Yeah, so this is so good. You know, it's like you guys are starting to piece together these pieces, right? And so you should feel pretty proud because, like I said, this is one of the harder things for a lot of students, right? So when we're adding electrons, it's real simple. You just add on, right? It's easy to add on. It's always a little harder to take away, okay? So if we're talking about, let's say we're talking about SI, and then we're going to go SI 4 minus. Okay. So what is the electron configuration for SI?
Ne. Uh, 3s2. Okay, then 3p.
3p2.
That's right, 3p2. Okay, so if we're going to Si4 minus, then what is it going to be?
Si4 minus.
We're
It's
adding
just
2 now, right? Instead of taking away. So we're going to add 4 to the
that's
P.
3p6.
So then my electron configuration should be Ne. Is that correct?
Or would we go to the next one because now aren't you going to be?
So we're here. This is where we're at. And so we're going to go use a different color.
But wouldn't you go up because now it wouldn't be 8, so wouldn't it be technically bringing you back to the next noble gas, or because it's the next oct whatever?
That's right. It would be the next noble gas. So you could. So you're asking me if I could just write it as Si. I mean that's Si4 minus, and sorry.
And just AR.
Yes, you could write it as that. Yeah, that would be
Okay.
acceptable. Or you could have written it as Ne.
3s2 3p all the way to 6.
That's right.
Okay.
Okay.
Dr. Henry,
Yes.
I have a question about the other, you say for F14, but how do you get 14?
Because in the f orbital, there is a total of 14 electrons that could be held up there. Remember, this guy here is the D. This is really the D orbital, right? So you see this blue spot here? That blue spot is technically where those guys actually go. But if you remember, I kind of showed this earlier. This is what the periodic table really looks like. Let's finish. Okay, so here's the 4F right here. You guys see it?
Yeah.
Okay, so we always have to fill up the 4F before we can get to the 5D.
Oh, okay.
Okay,
Okay, thank you.
no problem. Yeah, it's also, because if you guys blink, right, you'll miss something, right? It makes it a little harder in class. I mean, online. Or if you go take a potty break, you'll miss something.
Well, you gotta rewatch the videos multiple times.
Okay, so let's try one more and then we got to move forward. Okay, one more. We must. Let's see. Okay, we're gonna do a hard one. Oh, I know what we're gonna do. We're gonna do. We're gonna do. And that's a D, not a P. And then we'll do. DB. Okay, so if we're doing DB, what is my core, my noble gas?
Radon.
Okay, so DB is located here. So we have radon. Okay, and then
7s2.
Okay, and then
5f14.
Okay, 5f14. Okay, and then
Is it 73?
would it be 70 or would it be
6.
It's 63,
there
isn't
we
it?
go,
60.
six,
Yeah,
there we go,
63.
63.
Wait, I thought that's 62.
No, because remember you have one here, that's 1, that's 2, and that's 3.
Oh, okay.
Okay, so if I'm removing 3 electrons, so then what is it going to be? What is going to be my core?
Radon?
Sarah, what is the problem?
And then
Would you take off the 7s2 and then take 1 off of the 6d3?
that is correct. So we'd remove that guy and minus 1 from here. So then we'd be left with 5F, 14,
6d2.
6D2. Okay,
So are you always gonna just pretty much cancel out the first? Is that kind of like the kind of cancel the first 7? Yeah.
yeah. So you're going to cancel this guy out because he has a higher number.
Okay, I see. And then
Then you go to the next highest number, which is 6, right?
okay. And then you just subtract the 1.
That's right. Okay, so you're feeling pretty confident?
Someone asked, what is this process called? I'm curious too.
So all of this is called electron configuration. Now you're just doing electron configuration for ion. Okay. So I'm going to show you one more thing, and then
Henry, Dr. Henry,
yes.
in the case of this DB, you were actually moving backwards, like from 104, 103, you were going down, like lower in atomic number. You're actually moving backwards.
What are you talking about? What are you making reference to?
Okay, DB, not the DB3 plus, just the DB.
Okay.
You were actually going like, okay, DB, the atomic number is 103. Is that 103 or 105?
It's 105.
105. Okay.
Mhm.
So you were actually like, oh, okay. I see it now.
Remember, Mary, that place down there, it's like a whole, pretend it's in that little blue, like that whole strip, pretend it's in that blue section on the top.
Oh, okay.
Okay. Okay. How are you guys doing so far?
This is the first day the light bulb's been on.
I like it when the light bulb's on. Okay, so let's talk real quick about a couple of other things. So if we were talking about, let's say, nitrogen 3 minus, oxygen 2 minus, fluorine 1 minus. So all of these guys would have this electron configuration. Or it would be 1s2, 2s2, and 2p6. Okay, so, or we could just say neon. Then, of course, this is what neon's electron configuration is, right? So this term, the fact that they all have the same electron configuration is called isoelectronic. Okay, just basically meaning that they all have the same number of electrons. This guy is going to have a total of 10 electrons, neon. This guy is going to have a total number of electrons, 10 electrons. This guy has a total of number 10 electrons. This guy has the same number of electrons, 10, right? All together. Does that make sense? Yes, no, maybe?
Yes, sir.
Okay. So if you're asked if things are isoelectronic, meaning that they have the same electron configuration, you should be able to answer that, right? So if I asked you to identify
Oh, I was a little confused at first when I seen the F for the NE, but the negative, I'm just pretend it has a 1 right there, right?
Yeah, yeah. Okay. Can you tell me, can you circle all of the ones that are isoelectronic to each other?
Can potassium and sodium be one?
So you're saying, remember, this is potassium plus.
Yeah. Potassium
So
plus and sodium plus?
are they going to be the same? Are they going to have the same number of electrons?
Oh, no.
Okay, so what is the electron configuration for Ki? I mean, not Ki, K plus. Oop, yeah, so somebody said these two guys, that's true. Anything else on here? That have the exact same electron configuration. So let's circle them. Circle them in blue. So these two guys so far, anything else? Anything else is going to have the same electron configuration.
Would NA and NE have it that way as well?
Well, Na is not an ion, right? But Ne would have the same electron configuration as C4 minus and O2 minus. That's true. Oh, but you're saying Na plus? Is that what you're saying, Brittany?
Yeah, with the NE.
Yes, that's right. So all four of these guys would be, what about Al3 plus? Okay, so let's
Would it be with neon? Al plus with neon?
Yeah.
Okay.
Okay, so if we write the electron configuration for all of these, right? So neon is 1s2, 2s2, 2p6. Sodium is 1s2, 2s2, 2p6, and 3s1. So we know that that one doesn't, right? Right? Is it the same as neon?
No.
No.
No. Okay, so what about K plus? 1s2, 2s2, 2p6, 3s2, and now I'm running out of room. Oops, sorry. Three P6. Okay, is that the same as neon?
No.
No.
No. Okay. What about sodium plus? 1s2, 2s2, 2p6, and we got rid of this guy because we lost one electron. So is that the same as neon?
Yes.
Okay. Aluminum. 1s2, 2s2, 2p6. And then if you look where aluminum's at, it loses 3 electrons. 1, 2, 3. Oh my gosh, it's the same as neon. Okay. And then if we add 4 to this guy, 1, 2, 3, 4, same as neon. If we add 2, 1, 2, oh, same as neon. Okay, so that's an example of isoelectronic. So that's also kind of an example of the question that you guys are going to get. You got to get a list of a couple of things, and you got to try to figure out who are isoelectronic to each other. Does that make sense?
Yes.
Okay. So if it doesn't make sense, right, what you guys want to do is take a look at the chapter. We'll talk again. We'll briefly go over it a little bit on Thursday, and then we will start moving forward, and then you can talk to me in the lab, right? So we guys have to go to lab. So I'll meet you guys in lab.